Hello everyone, once again welcome back to our channel Beat the NEET. So हमारी ऑडियो बुक चल रही थी Haloalkanes and Haloarenes. इसमें हमने फर्स्ट पार्ट में रिटेंशन के पहले तक कवर कर लिया था एंड उसके आगे का मैं यहाँ पे स्टार्ट कर रही हूँ. तो बच्चों, दिस इज एन ऑडियो बुक, नॉट द एक्सप्लेनेटरी वन, सो बी स्पेसिफिक वेन एवर यू आर लिसनिंग इट. सो चलिए स्टार्ट करते हैं टाइम बिना वेस्ट किए. थर्ड पॉइंट, रिटेंशन. Retention of configuration is the preservation of the spatial arrangement of bonds to an asymmetric center during a chemical reaction or transformation. In general, if during a reaction no bond to the stereocenter is broken, the product will have the same general configuration of groups around the stereocenter as that of reactant. Such a reaction is said to proceed with the retention of the configuration. Consider as an example the reaction that takes place when 2-methyl-butane-1-ol is heated with concentrated hydrochloric acid. Here you can see this reaction. It is important to note that configuration at a symmetric center in the reactant and product is same, but the sign of optical rotation has changed in the product. This is so because two different compounds with same configuration at asymmetric center may have different optical rotation. One may be dextrorotatory plus sign of optical rotation, while other may be levorotatory negative sign of optical rotation. Number 4, inversion, retention and racemization. There are three outcomes for a reaction at an asymmetric carbon atom when a bond directly linked to an asymmetric carbon atom is broken. Consider the replacement of a group X by Y and in the following reaction. Here you can see this reaction. If A is the only compound obtained, the process is called retention of configuration. Here it is. Note that configuration has been rotated in A. If B is the only compound obtained, the process is called inversion of configuration. Here it is. Configuration has been inverted in B. You can see it is. That is completely inverted. If a 50-50 mixture of A and B is obtained, then the process is called Rasimization and the product is optically inactive. So one isomer will rotate the plane polarized light in the direction opposite to another. Now let us have a fresh look at SN1 and SN2 mechanisms by taking example of optically active alkyl halides. In case of optically active alkyl halides, the product formed as a result of SN2 mechanism has the inverted configuration as compared to the reactant. This is because the nucleophile attaches itself on the side opposite to the one where the halogen atom is present. When 2-bromo-octane is allowed to react with sodium hydroxide, octane 2 is formed with the OH group occupying the position opposite to what bromide had occupied. Here you can see this reaction. Thus, SN2 reactions of optically active halides are accompanied by inversion of configuration. In case of optically active alkyl halides, SN1 reactions are accompanied by racemization. Can you think of the reason why it happens? Actually, the carbocation formed in the slow step being sp2 hybridized is planar, that is achiral. The attack of the nucleophile may be accomplished from either side of the plane of carbocation, resulting in a mixture of products, one having the same configuration, the OH attaching on the same position as halide ion. Here you can see. And the other having opposite configuration, the OH attaching on the side opposite to halide ion. In the both I have shown you. This may be illustrated by hydrolysis of optically active 2-bromobutane, which results in the formation of plus minus butane 2-ol. Number 2, elimination reaction. But before that, here is the location of alpha and beta carbon in a molecule. Carbon on which halogen atom is directly attached is called alpha carbon. And the carbon atom adjacent to this called is the beta carbon. Here you can see this is just next to the halogen. So that is alpha carbon, then beta, then gamma. Number 2, elimination reactions. When a haloalkane with beta hydrogen atom is heated with alcoholic solution of potassium hydroxide, there is elimination of hydrogen atom from beta carbon and a halogen atom from the alpha carbon atom. Here you can see this reaction. As a result, an alkene is formed as a product. Since beta hydrogen atom is involved in elimination, it is often called beta elimination. If there is possibility of formation of more than one alkene due to the availability of more than one beta hydrogen atoms, usually one alkene is formed as the major product. These form part of a pattern first observed by Russian chemist Alexander Zaitsev, also pronounced as Sedzev, who in 1875 formulated a rule which can be summarized as in dehydrohalogenation reactions. The preferred product is that alkene which has a greater number of alkyl groups attached to the doubly bonded carbon atoms. Thus, 2-bromopentane gives penta-2-ene as the major product. Here you can see pent-2-ene, 2-bromopentane, and pent-1-ene, that is 19%. Here it is 81%. Now, elimination versus substitution. A chemical reaction is a result of competition. It is a race that is won by the fastest runner. A collection of molecules tend to do by and large what is easiest for them. An alkyl halide with beta hydrogen atoms, when reacted with a base or a nucleophile, has two competing routes: substitution, SN1 and SN2, and elimination. Which route will be taken up depends upon the nature of alkyl halide, strength, and size of base nucleophile and reaction conditions. Thus, a bulkier nucleophile will prefer to act as a base and abstracts a proton rather than approach a tetravalent carbon atom, steric reasons, and vice versa. Similarly, a primary alkyl halide will prefer a SN2 reaction, a secondary halide SN2 or elimination depending upon the strength of base nucleophile, and a tertiary halide SN1 or elimination depending upon the stability of carbocation or the more substituted alkene. Here you can see the elimination and substitution. Number 3, reaction with metals. Most organic chlorides, bromide and iodides react with certain metals to give compounds containing carbon-metal bonds. Such compounds are known as organometallic compounds. An important class of organometallic compounds discovered by Victor Grignard in 1900 is alkyl magnesium halide, RMGX, referred as Grignard reagents. These reagents are obtained by the reaction of haloalkanes with magnesium metal in dry ether, CH3CH2Br plus Mg in presence of dry ether, CH3CH2MgBr, and that is the Grignard reagent. Victor Grignard had a strange start in academic life for a chemist. He took a maths degree. When he eventually switched to chemistry, it was not to be the mathematical province of physical chemistry but to organic chemistry. While attempting to find an efficient catalyst for the process of methylation, he noted that zinc in diethyl ether had been used for this purpose and wondered whether the magnesium or ether combination might be successful. Grignard reagent was first reported in 1900 and Grignard used this work for his doctoral thesis in 1901. In 1910, Grignard obtained a professorship at the University of Tennessee, and in 1912 he was awarded the Nobel Prize for Chemistry, which he shared with Paul Sabatier, who had made advances in nickel-catalyzed hydrogenation. In the Grignard reagent, the carbon-magnesium bond is covalent but highly polar. With carbon pulling electrons from electropositive magnesium, the magnesium halogen bond is essentially ionic. Here you can see RMGX. Grignard reagents are highly reactive and react with any source of proton to give hydrocarbons. Even water, alcohols, amines are sufficiently acidic to convert them to corresponding hydrocarbons. RMGX plus H2O gives out Rx plus MgOHX. It is therefore necessary to avoid even traces of moisture from a Grignard reagent. That is why reaction is carried out in dry ether. On the other hand, this could be considered as one of the methods for converting halides to hydrocarbon. Wood's reaction. Alkyl halide react with sodium in dry ether to give hydrocarbons containing double the number of carbon atoms present in the halide. This reaction is known as Wood's reaction. Unit 13, Class 12. 2Rx plus 2Na gives out Rr plus 2NaX. This is very important reaction, bacho. 10.7.2 Reactions of haloarenes. Number 1, nucleophilic substitution. Aryl halides are extremely less reactive towards nucleophilic substitution reactions due to the following reasons. Number 1, resonance effect. In haloarenes, the electron pairs on halogen atom are in conjugation with pi electrons of the ring, and the following resonating structures are possible. Here you can see all possible resonating structures. CCl bond acquires a partial double bond character due to resonance. As a result, the bond cleavage in haloarene is difficult than haloalkane, and therefore they are less reactive towards nucleophilic substitution reaction. Number 2, difference in hybridization of carbon atom in CX bond. In haloalkane, the carbon atom attached to halogen is sp3 hybridized, while in case of haloarene, the carbon atom attached to halogen is sp2 hybridized. Here you can see. The sp2 hybridized carbon with a greater s character is more electronegative and can hold the electron pair of CX bond more tightly than sp3 hybridized carbon in haloalkane with less s character. The CCl bond length in haloalkane is 177 pm, while in haloarene is 169 pm. Since it is difficult to break a shorter bond than a longer bond, therefore haloarenes are less reactive than the haloalkanes towards nucleophilic substitution reaction. Number 3, instability of phenyl cation. In case of haloarenes, the phenyl cation formed as a result of self-ionization will not be stabilized by resonance, and therefore SN1 mechanism is ruled out. Number 4, because of the possible repulsion, it is less likely for the electron-rich nucleophile to approach electron-rich arenes. Replacement of hydroxyl group. Chlorobenzene can be converted into phenol by heating in aqueous sodium hydroxide solution at a temperature of 623 Kelvin and a pressure of 300 atmospheres. Here you can see this reaction. The presence of an electron withdrawing group NO2 at ortho and para positions increases the reactivity of haloarenes. Both reactions are here. Next reaction. The effect of pronounced when NO2 group is introduced at ortho and para position. However, no effect on reactivity of haloarenes is observed by the presence of electron withdrawing group at meta position. Mechanism of the reaction is as depicted. Here you can see the entire mechanism of the reaction. Can you think why does NO2 group show its effect only at ortho and para positions and not at meta positions? As shown, the presence of nitro group at ortho and para positions withdraws the electron density from the benzene ring and thus facilitates the attack of nucleophile on haloarene. The carbene ion thus formed is established through resonance. The negative charge appeared at ortho and para positions with respect to the halogen substituent is stabilized by NO2 group, while in case of meta-nitrobenzene, none of the resonating structures bear the negative charge on carbon atom bearing the NO2 group. Therefore, the presence of nitro group at meta positions does not stabilize the negative charge and no effect on reactivity is observed by the presence of NO2 group at meta position. Number 2, electrophilic substitution reactions. Haloarenes undergo the usual electrophilic reactions of the benzene ring such as halogenation, nitration, sulfonation and Friedel-Crafts reaction. Halogen atom, besides being slightly deactivating, is ortho-para directing. Therefore, further substitution occurs at ortho and para positions with respect to the halogen atom. The ortho-para directing influence of halogen atom can be easily understood if we consider the resonating structures of halobenzene as shown. Here you can see first, second, third, fourth structure. Due to resonance, the electron density increases more at ortho and para position than at meta positions. Further, the halogen atom, because of its minus inductive effect, has some tendency to withdraw electrons from the benzene ring. As a result, the ring gets somewhat deactivated as compared to benzene, and hence the electrophilic substitution reaction in haloarenes occurs slowly and require more drastic conditions as compared to those in benzene. Number 1, halogenation. You can see here the reaction. Next reaction is the nitration. You can see this reaction also here. Third one is sulfonation. The reaction is present here. Then after fourth, Friedel-Crafts reaction, and this is very important. Both reaction you can see. Number third, reaction with metals. Wurtz-Fittig reaction. A mixture of an alkyl halide and aryl halide gives an alkyl arene when treated with sodium in dry ether and is called Wurtz-Fittig reaction. You can see this reaction here. Fittig reaction, aryl halides also give analogous compounds when treated with sodium in dry ether, in which two aryl groups are joined together. It is called Fittig reaction. Here you can see. (10.8) Polyhalogen compound. Carbon compounds containing more than one halogen atom are usually referred to as polyhalogen compounds. Many of these compounds are useful in industry and agriculture. Some polyhalogen compounds are described in this section. 10.8.1 Dichloromethane, that is methylene chloride. Dichloromethane is widely used as a solvent, as a paint remover, as a propellant in aerosols, and as a process solvent in the manufacture of drugs. It is also used as a metal cleaning and finishing solvent. Methylene chloride harms the human central nervous system. Exposure to lower level of methylene chloride in air can lead to slightly impaired hearing and vision. Higher levels of methylene chloride in air causes dizziness, nausea, tingling, and numbness in the fingers and toes. In humans, direct skin contact with methylene chloride causes intense burning with mild redness of the skin. Direct contact with the eyes can burn the cornea. 10.8.2 Trichloromethane, that is chloroform. Chemically, chloroform is employed as a solvent for fats, alkaloids, iodine, and other substances. The major use of chloroform today is in the production of the Freon refrigerant R22. It was once used as a general anesthetic in surgery but has been replaced by less toxic, safer anesthetics such as ether. As might be expected from its use as anesthetic, inhaling chloroform vapors depresses the central nervous system. Breathing about 900 parts of the chloroform per million parts of air for a short time can cause dizziness, fatigue, and headache. Chronic chloroform exposure may cause damage to the liver, where chloroform is metabolized to phosgene, and to the kidneys, and some people develop sores when the skin is immersed in chloroform. Chloroform is slowly oxidized by air in the presence of light to an extremely poisonous gas, carbonyl chloride, also known as phosgene. It is therefore stored in closed dark-colored bottles completely filled so that air is kept out. 2CHCl3 plus O2 in presence of light, it is forming 2COCl2, that is phosgene, plus 2HCl. 10.8.3 Triiodomethane, that is iodoform. It was used earlier as an antiseptic, but the antiseptic properties are due to the liberation of free iodine and not due to iodoform itself. Due to its objectionable smell, it has been replaceable by other formulations containing iodine. 10.8.4 Tetrachloromethane, that is carbon tetrachloride. It is produced in large quantities for use in the manufacture of refrigerants and propellants for aerosol cans. It is also used as feedstock in the synthesis of chlorofluorocarbons (CFC) and other chemicals, pharmaceutical manufacturing, and general solvent use. Until the mid-1960s, it was also widely used as a cleaning fluid, both in industry as a degreasing agent and in the home as a spot remover and as fire extinguisher. There is some evidence that exposure to carbon tetrachloride causes liver cancer in humans. The most common effects are dizziness, lightheadedness, nausea, vomiting, which can cause permanent damage to nerve cells. In severe cases, these effects can lead rapidly to stupor, coma, unconsciousness, or death. Exposure to CCl4 can make the heart beat irregularly or stop. The chemical may irritate the eyes on contact. When carbon tetrachloride is released into the air, it rises to the atmosphere and depletes the ozone layer. Depletion of the ozone layer is believed to increase human exposure to ultraviolet rays, leading to increased skin cancer, eye diseases and disorders, and possible disruption of the immune system. 10.8.5 Freons. The chlorofluorocarbon compounds of methane and ethane are collectively known as freons. They are extremely stable, unreactive, non-toxic, non-corrosive and easily liquefiable gases. Freon 12CCl2F2 is one of the most common freons in industrial use. It is manufactured from tetrachloromethane by Schwartz reaction. These are usually produced for aerosols, propellants, refrigeration and air conditioning purposes. By 1974, total freon production in the world was about 2 billion pounds annually. Most freon, even that used in refrigeration, eventually makes its way into the atmosphere, where it diffuses unchanged into the stratosphere. In a stratosphere, freon is able to initiate radical chain reaction that can upset the natural ozone balance. Unit 14, Class 12. 10.8.6 DDT. DDT, the first chlorinated organic insecticides, was originally prepared in 1873, but it was not until 1939 that Paul Muller of GG Pharmaceuticals in Switzerland discovered the effectiveness of DDT as an insecticide. Paul Muller was awarded the Nobel Prize in Medicine and Physiology in 1948 for the discovery. The use of DDT increased enormously on a worldwide basis after World War II, primarily because of its effectiveness against the mosquito that spreads malaria and lice that carry typhus. However, problems related to extensive use of DDT began to appear in the late 1940s. Many species of insects developed resistance to DDT, and it was also discovered to have a high toxicity towards fish. The chemical stability of DDT and its fat solubility compounded the problem. DDT is not metabolized very rapidly by animals. Instead, it is deposited and stored in fatty tissues. If ingestion continues at a steady rate, DDT builds up within the animal over time. The use of DDT was banned in the United States in 1973, although it is still in use in some other parts of the world. Here you can see the structure of DDT. Summary: alkyl aryl halides may be classified as mono, di or polyhalogen, tri, tetra, etc. compounds depending on whether they contain 1, 2 or more halogen atoms in their structures. Since halogen atoms are more electronegative than carbon, the carbon-halogen bond of alkyl halide is polarized. The carbon atom bears a partial positive charge and the halogen atom bears a partial negative charge. Alkyl halides are prepared by the free radical halogenation of alkanes, addition of halogen acids to alkenes, replacement of OH group of alcohols with halogens using phosphorus halides, thionyl chloride or halogen acid. Aryl halides are prepared by electrophilic substitution to arenes. Fluorides and iodides are best prepared by halogen exchange method. The boiling points of organohalogen compounds are comparatively higher than the corresponding hydrocarbons because of a strong dipole-dipole and van der Waals forces of attraction. These are slightly soluble in water but completely soluble in organic solvent. The polarity of carbon-halogen bond of alkyl halides is responsible for their nucleophilic substitution, elimination, and their reaction with metal atoms to form organometallic compounds. Nucleophilic substitution reactions are categorized into SN1 and SN2 on the basis of their kinetic properties. Chirality has a profound role in understanding the reaction mechanism of SN1 and SN2 reactions. SN2 reactions of chiral alkyl halides are characterized by the inversion of configuration, while SN1 reactions are characterized by racemization. A number of polyhalogen compounds, example dichloromethane, chloroform, iodoform, carbon tetrachloride, freon and DDT have many industrial applications. However, some of these compounds cannot be easily decomposed and even cause depletion of ozone layer and are proving environmental hazards. Thank you so much.